Young's double slit. Young's double slit. In 1801, Thomas Young first demonstrated experimentally the phenomena of interference of light. What is interference of light? If two or more light waves with the same phase, same frequency, same amplitude superimposed to each other, then it produces maximum and minimum intensity fringes of light produces on the screen. Phenomena is called interference of light. So first demonstrated, the Young gave the first experimental evidence of interference of light. Interference of light. In 1801, Thomas Young first demonstrated experimentally the phenomena of interference of light. When sunlight passes through pinhole, you can see here in 1801, Thomas Young. So here, Thomas Young first demonstrated experimentally the phenomena of interference of light. So this is the S is the source of light. S is the source of when sunlight is allowed to fall on the, so this is the sunlight is allowed to fall on the slit S. When sunlight passes through pinhole S, so spherical waves are spread out. You see here, these are the spherical waves. These spherical waves are spread out. These spherical waves are allowed to fall on the S1, S2 slits. You can observe in figure. So these spherical waves also spread out from pinholes S1 and S2. You observe, so these spherical waves are also moving from one place to another place. The radii of these wave fronts increases, you can observe, increases as they move away from S1 and S2. Hence they superimpose on each other and alternative bright and dark, bright and dark, bright and dark. So bright and dark fringes are observed on the screen, XY screen, placed at a distance of D. So from this place to screen place, the distance is capital D. Distance, capital D. If crest of one wave falls on the crest of other wave, or trough of one wave falls on the trough of other wave, then the resultant amplitude and intensity is maximum. It is called constructive interference. If crest of one wave falls on the trough of another wave, or trough of one wave falls on the crest of another wave, it produces minimum intensity fringes. Minimum intensity means dark fringes. So this is minimum intensity. Minimum intensity fringe means dark fringe. Maximum intensity fringe means bright fringe. So when crust falls on the trough or trough falls on the crust, so it gives the minimum intensity fringe on the screen. That is destructive interference. Destructive interference. What I am saying, so S is the slit, pinhole slit. When sunlight passes through this pinhole slit, the spherical waves are moving from the slit. So these are allowed to fall on the S1, S2 pinhole slits. From pinhole slits also, the spherical waves are produced. This spherical waves radii increases. These are superimposed to each other and gives rise to bright and dark fringes on the screen. Dark and bright fringes on the screen. If crust falls on the crust or trough falls on the trough, then it produces maximum intensity fringe, bright fringe on the screen phenomena is called constructive interference. If crust of one wave combined with trough of another wave, so trough of one wave falls on the crust of another wave, it produces minimum intensity. So it gives the dark fringe on the screen. On the screen phenomena is called destructive interference. So in general, we can draw here. I am drawing this Young's double slit experiment. You try to draw this figure here. I am taking and drawing. So you just observe here. So I am taking and drawing here. So just take your notebook, rough notebook, and draw it. Very, very important. So it will come in your examination. So try to yes. Take one straight line. First to take one straight line. Yes. Take one straight line. Yes. So this is the pinhole. This is pinhole S. Pinhole S. From the pinhole, a spherical wave is produced. So this is the spherical wave. So this is another pinhole S1. This is S2. From these pinholes also spherical wave is produced. So this radii increases. You take here carefully, this is dot, this is 0, this is dot, this is 0. So festival is coming Sankranti, this is Sankranti Mugu. You can observe here. So dot, this is 0. Sukha Sunna Mugu. You observe here. This is dot, this is 0. This is 0. This is dot, this is dot, this is 0. So you take 0, dot, dot, 0. So this is 0, dot, dot, 0. So this is 0, dot, dot, 0. You can take any number of like this. Yes. So in between these 4 dots, you take another 0. You take another 0. So this is the Sukkala Mugu. Right? So this is coincide, superimposed to each other. 1 second. Yes. Superimposed to each other. You see carefully. So this is Chukka Sunna. Sunna Sukka. Just take it. So just you carefully take 0, dot, 0, dot, 0. 0, dot, 0, dot, 0. So 0, dot, 0, dot, 0. So now here you can take, so this is dot, 0 and 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 dot. So 0 and dot, this dot 0 we can take. Here also same. So dot 0, dot 0, 0 dot, dot 0, 0 dot. So dot 0, 0 dot, dot 0, 0 dot, dot 0, 0 dot. So this is the interference. So I am taking here I am taking here some line. So this is XY screen. This is X. This is Y. So this is the interference pattern. Interference pattern. You can draw yourself in your examination. I showed clearly. So I will give this figure in our notes. So same. So this is S. Sunlight is allowed to fall on the pinhole slit S. So from this pinhole, a spherical wave is produced. It is allowed to fall on the S1, S2 slits. You can see here S1, S2 slits. From this S1 and S2 slits also, a spherical wave is produced. This spherical wave is superimposed to each other. Superimposed to each other. So if crust is combined with crust, or trough is combined with a trough, it produces dark, maximum intensity fringe on the screen. That is called bright fringe. That is called constructive interference. Constructive interference. If crust of one wave combined with the trough of another wave, or trough of one wave combined with the crust of another wave, it produces minimum intensity dark fringe on the screen. It gives the minimum intensity. This phenomena is called destructive interference. Destructive interference, you see here. So this is the actual pattern. Actual pattern. So this dot represents dark, represents bright fringe. So this is in our zero, that represents. So this is represents. This is here. This is dark. This is bright. So we observe alternative bright and dark. Bright and dark. Bright and dark. So this is the interference pattern in Young's double slit. Young's double slit. So we can draw like this. You see here, from Huygens principle, each point on the wavefront is a secondary wavelet. The radii of this wavefront increase as they move away from S1 and S2, and hence they superimpose on each other, and alternative bright and dark fringes are observed on the screen XY, placed at a distance capital D from S1 and S2. At a point where a crust due to one wave falls on the crust due to another wave, the resultant displacement is sum of the amplitude due to each wave separately. This is known as constructive interference. You can observe this is destructive interference. Destructive interference at points where a crust due to one wave falls on the trough of another wave. The resultant amplitude is equal to the difference of amplitudes due to the each wave separately. This is known as of amplitudes due to each wave separately. It is known as destructive interference. On the screen, a number of alternative bright and dark regions of equal width called interference fringes are observed. Interference in thin film by reflection. Interference in thin film by reflection. The example of interference in thin film, that is Newton rings. So you observe here interference in thin film by reflection. Thin film, for example, this is one film you observe in your old camera. Some film is there like that. So just you can take it has upper surface and lower surface. So in between some thickness is there. You can observe some thickness. So that is just thin film. That is thin film. When light is incident on a plane parallel thin film, some portion of light gets reflection from the upper surface. You can see. So this is AB is the monochromatic light is incident on the upper. You see here JK upper surface of thin film, J1 K1 is the lower surface of thin film. You can see here JK J1 K1 be the two surfaces to a transparent thin film. You can write in your own words. JK is the upper surface, J1 K1 is the lower surface of the thin film. Let small t, not smarty, small t is the thickness of this thin film. Mu is the refractive index. Mu is the refractive index. Let a monochromatic light ray AB is incident on the upper surface with the incident angle I. So some portion of this transmitted, this is transmitted BC as BC, some portion of light ray reflected as BE. So AB light, monochromatic light is incident on the upper surface, some portion reflected as BE, some portion of light transmitted through the BC. It is incident on the lower surface. It is also reflected as CDF. You can observe here. So here. When light is incident on a plane parallel thin film, some portion of light gets reflection from the upper surface and the remaining portion of light is transmitted into the thin film. Again, some portion of transmitted light is reflected back into the film by the lower surface and emerges through the upper surface. Up to here, I explained. These reflected light beams superimpose with each other, producing interference and forming interference phenomena or pattern is called interference in thin film by reflection. So this is the definition. You can see here. Simply, this is definition. So what I am saying, AB, monochromatic light is incident on the upper surface with incident angle I. Some portion of light reflected as BE, that is ray 1. Remaining monochromatic light transmitted through the thin film and incident on the lower surface. It is also reflected from the lower surface and from the emerges upper surface and comes out as DF or ray 2. This ray 1 and ray 2 superimpose to each other and gives rise to interference pattern phenomena is called interference in thin film by reflection. Let JK, J1, K1 be the two surfaces. So mu is the refractive index, T is the thickness of the sample. You can see here. You can see. So just observe. I am going to draw this. You take your pen and paper. I am going to drawing here. So you take one line. This is J. This is K. JK. This is upper surface. upper surface. So I am going to take another one. So this is lower surface. This is J1, K1. This is lower surface. Lower surface. So here this is small t, not smarty, small t. That is the thickness of this thin film. Mu is the refractive index. Refractive index. So here, this is the normal line. You can observe this is the normal line. So the light AB, monochromatic light, is incident on the upper surface with the initial angle I. Initial angle I. So some portion of this light reflected, some portion of this light reflected as BE. As BE. So remaining portion of light transmitted and incident on the lower surface. It is also emerges out as F. So it is incident on D. D. So we can also prepare here another triangle. This is one triangle. So here also we can prepare in air. This is another triangle. So this is B, C, D, E, F. This is G. So here this is H. H. So here also same incident angle, same like this AB. FD also same like this. We can write this is I. So incident with I, refraction angle small r. So this is also small r, small r. This is the right angle. Right angle. So same figure you can observe here. Same figure you can observe here. So you can see here BE, the AB monochromatic ray is incident on the upper surface at point B with incident angle I. Some portion of light reflected as BE, remaining ray transmitted through the thin film, it is incident at lower surface at point C. It is also reflected from lower surface and emerges from upper surface as DF. So we can take this is initial angle, refraction angle, this is initial angle. We can made another triangle in air. Let angle of refraction smaller. The ray BC will be reflected into the film and emerges through the as DF. Already I told. These two light rays superimpose and depending upon the path difference between then the producing interference pattern. So to know the path difference, let us draw the normal DG. You see, this is DG to BE on BE. From the points D and G onwards, the light rays travels equal distance by the time the light rays travels from B to G. The transmitted light ray has to travel from B to C and C to D. You write in your own words. What I am saying, AB light ray, monochromatic light ray is incident on the upper surface at point B with incident angle I. Some portion of light reflected as BE remaining transmitted through the thin film and incident at lower point C. It reflected and emerges from capital D as DF. So ray 1 and ray 2 have the phase difference pi, path difference lambda 2. So these are superimposed to each other and gives rise to interference pattern. Up to here, that is the interference pattern. The path difference between two reflected light rays, ray 1 and ray 2, this ray 1 and ray 2 path difference is given by the path difference is equal to mu, refractive index mu into this BC plus CD. BC plus CD in film minus BG. You observe clearly here, this part from here to here, this same part we can assume inside the film. So this is the path difference. This part is path difference. Path difference. So we get this value, this value. So from this total BCD, we should remove this point, this value. We should remove. So minus BG. So I am taking from here to here. I am removing this BG. This BG and this one. If we get this value, we should remove this from this arrow to this arrow. That is equal to BG. This is BG equal to BG. So what I am saying, minus BG in air. Simply you remember the path difference. The path difference between two reflected light rays, ray 1, ray 2 is given by mu into BC plus CD in film minus BG in air. That is equation number 1. Equation number 1. Okay, you see here, from the triangle, we are going to calculate BC value. From the triangle BCH, I want to cos R. Cos R is equal to opposite side BH. 1 second. So here, this is the right angle. We can take, this is the angle. So we are taking here. So this is HC. This is the adjacent side, not opposite, adjacent side by hypotenuse BC. Cos R is equal to adjacent side by hypotenuse. So HC by BC. What is this HC value? T, thickness. So I am substituting here. Cos R is equal to HC by BC, T by BC. So BC is equal to T by cos R. That is equation number 2. So another triangle, this is DCH. DCH. I want to take same cos R. Cos R is equal to adjacent side, HC by hypotenuse, this is CD. So T by CD, CD is equal to T by cos R, as it is I am taking here. Calculation of BG. This is BG. So we want to calculate this BC, CD and BG. So I calculated here BC and also CD. Now I am going to calculate BG. From the triangle BGD, I want to take sin I. Sin I is equal to opposite side BG by hypotenuse BD. Hypotenuse BD. So BG is equal to, we can write BD sin theta, equation number 4. But what about BD? Up to here, BH plus HD. BH plus HD, this is equation number 5. From the triangle BHC, you observe here BHC, another triangle. Tan, I want to take tan R. Tan R is equal to tan r is equal to, we can take opposite side by adjacent side. So this is BH by CH. So BH by what is CH? Again, this is small t. So BH is equal to T tan R. T tan R. Similarly, triangle, this DHC, we can take tan R. That is HD by CH, HD by T. So HD is equal to small t into tan TR. Now substituting this BH value and HD value in equation 5. So BD is equal to, this is tan T into tan TR plus T into tan TR. BD is equal to 2T tan R. 2T tan R. This is equation number 1. Now substituting this equation 6 in equation 4 at the place of BD. At the place of BD, we can substitute, you observe here. Now substituting equation 6 in equation 4. So BG is equal to, this is 2D. So this is what I am saying here, equation 4. So BD into sin I. So this is BD into sin I. Okay. So according to Snell's law, sin I by sin R is equal to mu. You know very well. From this relation, sin I is equal to mu sin R. So substituting at the place of sin I, you should take mu sin R. So BG is equal to 2. You see here. So BG is equal to 2T tan R sin I. So 2T tan R as it is. What is sin I? Mu sin R. So 2 into this mu, I am taking here 2 mu T tan R into sin R. That is equation number 7. You observe here, equation number 7. Now substituting equation 2, 3, 7 in equation 1. So equation 2, 3 in 7. Equation 2, BC is equal to T by cos R. This is equation number 2, cos R. So CD is equal to T by cos R. This is equation number 3. Equation number 3. So equation 7 you can observe here. This equation 2, 3, 7, we should substitute in equation 1. This is the equation 1. This is the equation 1. So path difference I am taking here. Path difference is equal to mu as it is. So BC we should substitute T by cos R plus CD T by cos R minus as it is minus. What is BG? This equation 7 as it is substitution. 2 mu T tan R sin R. So we can write this is 2 mu T cos R, because you see here, so T plus T by cos R plus T by cos R. This is 2T by cos R inside 2T by cos R. We can write 2 mu T cos R minus, this is as it is. As it is. So 2 mu T cos R, this is 2 mu T as it is up to here, 2 mu T. Here same. What is tan? Tan R is equal to, I am writing here, sin R by cos R. You can observe here. So remaining same. This is same, 2 mu T cos R minus 2 mu T sin R into sin R, sin square R by cos R. So just to take a common factor, 2 mu T cos R. So here 2 mu T cos R. Remaining 2 mu T cos R, 1 minus sin square R. What about 1 minus sin square R? That is cos square R. So I am substituting here cos square r. This cos r, this is square gets cancelled. So path difference is equal to 2 mu t cos r. Path difference is equal to 2 mu t cos r. The light ray 1 undergoes an additional phase exchange pi or additional path difference lambda by 2. So just additional, just you add here the path difference, total path difference is equal to 2 mu t cos r plus lambda by 2. The rate to move additional phase difference pi or additional path difference lambda by 2, lambda by 2, just add it. So total path difference is equal to 2 mu t cos r plus lambda by 2. So condition for bright fringe. Condition for bright fringe. In general, bright fringe path difference n lambda. We studied in our Young's double slit. Young's double slit. So the ray 1 and ray 2 meet in phase and undergoes constructive interference. So it gives the bright fringe. Bright fringe. So this is the 2 mu t cos r. The path difference is equal to n lambda. Here path difference, what is this? 2 mu t cos r plus lambda by 2. Lambda by 2. In general, path difference n lambda. So just to take both. Here, this is n lambda minus lambda by 2. You can write 2n minus 1 lambda by 2, where n is equal to 0, 1, 2, 3, and so on. The condition for bright fringe 2 mu t cos r, that is equal to 2n minus 1 into lambda by 2. So condition for dark fringe, when the path difference is equal to, this is the general in Young's double slit, then ray 1 and ray 2 meet out of phase, it gives the destructive interference. So dark means, so out of phase, so undergoes destructive interference. 2 mu t cos r plus lambda by 2, this is the path difference here. So this is the condition, 2n plus 1 lambda by 2. This is 2n plus 1 lambda by 2 minus this lambda by 2. So common lambda by 2, 2n plus 1 minus 1 plus 1 gets cancelled. We get 2n lambda by 2, 2 gets cancelled. 2 mu t cos r is equal to n lambda. This is the condition for dark fringe. Depending on above conditions, the interference pattern consists of bright and dark fringes. It gives interference pattern. The example of interference in thin film is Newton rings.